So the goal today is to cover mechanism design as one of the tools that sort of another interesting tool, at least from my point of view, combination of some of the ideas we've covered already, and things like social choice and voting and things like that, with some ideas from game theory, which we alluded to at the end of some of the voting lectures, but connects to both social choice and game theory. We'll try to make clear what those connections are. Building off of, at some point, some of the work we talk about today, we'll build off of what we worked on earlier. I should definitely not use this. What we've worked on earlier tied to asking questions about bandits, preference modeling, preference optimization. We'll think of similar ideas, but now in a strategic or game theoretic setting with actors that may be adversarial or may be facetious in various ways. And so hopefully some of this frame will be clear by the end of the lecture today. So in terms of a bit of frame setting, for those of you who haven't seen mechanism design before. So one of the definitions, or some of how the field defines itself, is in terms of the science of rulemaking. So thinking about this as how one can design rules such that you get design rules such that even if participants choose to be strategic meaning that the way that they engage in the system could include, for instance, being adversarial or being like targeting their own preferences, or it's like whatever way that they choose to engage. The overall ecosystem still sort of worked correctly to lead to some desirable outcome, which is a social choice kind of setting. Just like in social choice, part of the role of the designer is to decide what desirable outcome is. And beyond that, then the job is to figure out what are the interventions that one can, or how can one decide the rules of the game, if you like, or the rules of the interaction, such that you get at that desirable outcome, even if the actors in that outcome choose to be adversarial or strategic in various ways. So that's sort of the broad framing of what this field tries to answer. So I'll try to make this a bit clearer, maybe grounding examples as we go through. It borrows from a bunch of different, fields of study. So traditionally mostly studied in economics, borrows a bunch from game theory ideas. I don't know the actual length of time, but I want to say definitely in recent memory, roughly aligned with when sort of large internet companies became a thing. It ended up being extremely useful for real world sort of computing tasks. And so it became a topic that was studied more and more in computing literature. And so we'll touch on some of these today, but this include things like what came up with social choice, the notions of computational complexity, but also interesting questions of if a machine learning model is part of the mechanism, how do I think about its learning process within the mechanism? Again, hopefully some of this will be clearer over the course of the lecture today. So I'll talk through some of the real world impact, but I think one of the clearest successes, and actually one of the ideas we'll spend the most time on today, are things like auctions and various kinds of pricing and economic decision making, where there's been a ton of impact of both designing mechanisms or studying their properties in various kinds of real world contexts. So I'm showing here an example of an auction, that's a literal auction, to give maybe a flavor of some of what we'll discuss in the next few minutes. So I'll start off with some of the existing examples of where mechanism design ideas, auction ideas have had impact. So the examples from things like when there was a bidding auction process for when some of the spectrum for radio waves was deregulation change. There's a bunch of work that used ideas of mechanism design to sort of set up a bidding process such that even if the actors, in fact, clearly the actors were self-interested, right? They want to maximize profit or whatever. Yet you want to set up a process such that you're likely to get good outcomes. So again, framing what mechanism design tries to do. So these are good references if you're interested in some of the history. These kinds of ideas, and particularly things like auctions and pricing, are used a ton in lots of web companies. So allude to the example I gave earlier. Things like Amazon deciding sort of pricing and ordering of items and things like that. A lot of the big web search companies use ideas borrowed from this literature. So Google uses this as one of the things that powers the ad buying process behind search. And I like these numbers. I'm borrowing this from a colleague who gave this talk initially. The references at the end. But in 2016, Google had a $79 billion revenue in ads. Total revenue was 89.6, 79 So something like, definitely the vast majority of their revenue was tied to ads, and this technology powered by, again, sort of auction processes and bidding process and things like that. Facebook, similarly, I think, again, ad revenue in 2016, everything else was a rounding error compared to like what was tied to ad revenue. And what powers the ad process are auction kind of ideas that come from mechanism design. Many of them directly borrowing, some of them small adjustments. Again, we'll get to some of this over the course of the lecture today. So the main point being made here is that this is an area that particularly in recent times, has had a huge impact on society generally, because the tools that it brings have now been used for lots of pricing kinds of decisions, auctions, collective decision-making of various kinds. Okay, so for our purposes, and maybe to be more direct, the key question, or one question that you might be interested in asking that may lead you to using some of these tools are questions like, can we infer biased true economic preferences? And economic preferences, I'm thinking here of as like, what actual value or price do different stakeholders have, in this case buyers have, for certain items that you may be looking to sell. And so if this is a setting that you're in and you're going to use a mechanism, then the mechanism needs to decide which buyers receive what items and then how much they pay for each one of these items. And the goal under the hood is to do it in such a way that, again, you could define a societally desirable outcome. Often in these settings, a societally desirable outcome is that the amount paid is commensurate with the value of actual items for individuals. And like an economically good outcome might be whoever values the item the most actually gets to win a bid for that item if they bid their true value for that item. So for example, in a coffee shop setting, an item could be coffee, cupcake, or coffee and cupcake. And we have two potential buyers who have different prices for like what they think a coffee is worth, cupcake is worth, meaning how much they'd be willing to pay, right? Or the combination of coffee and cupcake. And the task might be, or the task here, the mechanism's task is to figure out how do I design the interaction system such that, for instance, if you're comparing just the cupcake, the individual who values cupcake the most might win the bid. And it's worth stating that individuals or buyers here have incentive to be strategic, right? So they want the item, but they also want to pay as little as they want, as they can, right? So there's this tension of, if you like trying to game the system in some sense and pay as little as possible, but also having some intrinsic value for the set of items that are being sold here. Does this make sense as a general framing? Yes, please.
So in here, like this example, the cupcake one, person is willing to pay $3 right, to the other at $2. So as like we think, okay, $2 is the price, we are kind of exploiting that one person to give as max he could, like that is 3. So in like a social setup, like
is that a good outcome?
Cake prices too, right. But we are just exploiting that how much a user is willing to pay and then go till 3. Is that like?
I think that's an interesting. So maybe at a very high level, it's up to the designer to decide what a socially valuable outcome is. I think many of the framings of this problem use maximal revenue essentially as the desirable outcome. And so in that setting, then just maximizing the price paid would be the thing you're aiming for. I think at a very, very high level, like somewhat beyond the scope of this class, a lot of what we said from social choice also applies here. As a designer, it's part of your goal, your job to decide what the desirable outcome is. And so you could decide to design a mechanism such that you get at different goals than maximizing revenue. That said, we'll engage a bit. Most of the things we'll talk about today, most of it will engage with strategic behavior of the actors and how we can make sure we avoid being fooled by strategic behavior. But I think it will be framed around maximizing revenue as societal good. There are other notions of this that tie to things like welfare, which is not that different, sort of some difference of cost and revenue. And again, at the 10,000 foot view, a designer could pick a different social outcome as like what they consider social good, and for that outcome, design a mechanism to get at it. So if you like, this flexibility in design there. But I think in practice, and maybe not surprisingly for, say, economic folks, it's maybe not super kind of obvious that they might think of revenue maximization as a good outcome. And I mean, we're not going deep into this, but there are philosophical arguments for why people might think capitalist-style revenue maximization is like a good way to design markets, good way to design a bunch of other stuff. So we won't go into that very much. We'll borrow a lot from that literature, and I'm maybe spending too much time on this. But I guess I'll say at a high level that there are avenues to think of other good outcomes and design for those. It's a good question. Thank you for asking. Okay. Other thoughts? Okay. Hopefully it's also clear how this ties to preferences, because again, if you think of preferences as being economic or can be economically priced or judged or valued, then preferences are now grounded here as like prices people are willing to pay for certain items. So it's maybe incomplete in the whole frame of this class, because we talked about lots of different kinds of preferences, and many that don't seem as obviously quantifiable economically. But for most of what we covered today, and for many applications, and particularly when you can ground things economically, this approach can be very useful. So it's a bit more general, but I think this is the easiest way to have the discussion. So I think we'll mostly. So I guess I should also say that this is a topic. It's like almost like everything else we've covered. It's an entire field, right? And even here, there are entire classes on it. And I'm only touching the surface of the material. So I'm hoping to inform on, particularly folks who are not aware, on how this might be interesting, how it informs our questions of eliciting preferences and social choice kinds of questions. And then if people are interested, like I'll have references so you can dig more deeply and think through some further stuff. Okay, so, this is the framing, this is the setting. There are a bunch of stuff you could do. There's a very, very obvious standard thing that you could do to sort of decide on how you might do the thing that the mechanism has to do, which is which buyers receive items versus and or what they pay. I guess throwing out loud thoughts on how you might decide on how to sell items to these people. Assuming these are the people, these are the buyers, you're the designer. Let's say you're going with, I want to maximize revenue for now. What might be some ways that you might decide on, what mechanism might you design such that people can engage in this activity? There's a obvious, non-interesting, obvious one, which is what happens in most places that are not auctions, which is, you post some price and people would just sort of decide or not to buy the items based on their value. Often we think about this as an individual level. We think about this as utility. So, post this price might be, I choose $150 for the coffee, $350 for the cupcake, and I maybe price this individually. So the combination is just the sum of the cost. Whereas for an individual, the price or their value for coffee and cupcakes together is actually different from separately. You can think about this might happen easily for lots of different kinds of economic decision making. And so in this setting, the individual, I think 350 plus 150 is less than their 6, so they'll probably buy. To them, they've increased their utility, right? Because they're willing to pay 6. Your total price for the item together is 5. So the price is less than their internal utility, or the internal value, and so the utility here would be 6 minus 5 is 1. That's sort of their win. Yes.
So the price is an additive? Like, I'm confused.
Oh, that's a good question. So in this example, and the framing more generally, and I should also, I'll state this here, and then I'll try to bridge this more generally. So the setup allows for prices across sets of items that are not additive. And it seems to match lots of real world behavior where people value sets of things differently than individual things. Maybe, so let me attempt a coffee cake. I mean, you can imagine practically that this might be true. Like you may have a situation where you actually need both and you're not happy with either. And you might pick a place that will have both. You can imagine this as a real world decision making. But the other resourcing things, I don't know. You're picking a class and you have to decide instructor, who you might work with on a course project, computing resources. There's some pricing for each thing individually. You can imagine there's some pricing for having actually those things jointly, like at the right configuration of those things. That's very different from each thing individually because each thing blocks each other a little bit. And so the right answer is a combination and you need to match your combination. So your pricing for getting the combination right is much higher than getting a good instructor you like. I don't know. Your friends taking the class or on a class offering, promising that they give you 10 GPUs per student to do whatever you like. Each individually, these make sense. And for some decision makers, single issue, if you give me enough GPUs, I don't care about the rest of it. Or my friends are taking a class, I don't care about the rest of it. But I'd argue for many of us, really the combination. And so we're doing trade-offs across these things. And the trade-offs may not be additive. So the combination might actually have a different value in real thing. So maybe just to frame your question. But more generally, the framework allows for settings where combinations are not necessarily additive in components. It's a good question. Other thoughts or questions? Okay, so this is maybe the standard thing. This is what happens in most places. What you get at the end is that if someone purchases your item at a certain price, if you're thinking purely economically, what you know is that their value must be higher than your stated price. So you learn at least that much, like an ordering thing. Because otherwise, under this model, they will not buy your item, right? It needs to be that they have positive utility. So you don't learn that much about individual preferences, but you learn some, at least, directional signal about how they value the thing that they bought. Does that make sense? Okay, so you might do something else. You might do an auction. So this is, you have your item, everyone gets to bid on the set of items, and whoever has the winning bid gets the item. So this is maybe a standard, again, to some extent thing. To some extent, you might imagine that if you deploy this, you get maybe more signal about people's actual value for the item because you would imagine or hope that they would bid something correlated with how much they actually value the item. They might not. And in fact, this is a lot of the literature and engagement here is, again, engaging with what might individual buyers do in this setting and how might they try to game this system. Any thoughts? So if you were bidding on an item in this class, 6 7 people, at least in person here, and we all have chosen to buy the Mona Lisa for whatever reason, and we can afford it also. Some of you might, I cannot afford the Mona Lisa, but I don't think you can buy it. Do a standard bid, standard auction. Thoughts on how if you wanted to be strategic and maybe get the item cheaper, perhaps, what might you do?
Yeah. I mean, you only bid like the minimum amount you have to top.
Yeah, so you sort of figure out if you're the last person to bid in particular. So you try to order information such that you get the most information, you get what everyone else is willing to bid. Your actual value may be higher. If your value is higher than whatever is the current maximum price, you just go a little bit above, you win the bid. That seems like for the individual who is being strategic, this seems a very reasonable thing to do. So, if you're thinking of social welfare as maximum revenue, that's a bad outcome. If you're thinking of the goal of figuring out people's true utilities or value for things, it's maybe not ideal as well, because then people are incentivized not necessarily to bid their true value. They're incentivized to bid to win, and winning is just different than actually bidding what they value the item as. Any other thoughts on other strategic behavior that you could do? I think that's the obvious one, but for others. Okay, I'll have you think about it. I think we'll get to it in some of the other discussion that we have. Another auction, one that you might have seen and is quite popular, is a second price auction. So what you do is everyone bids. This partially mitigates the strategy that you just talked about. Everyone bids. You get all the bids together, but the amount you pay is not the highest bid. You pay the second highest bid. Why might this be interesting?
Some sort of a tie.
Yeah, so a tie is interesting. I think that's a little bit separate from this. Let's assume, for discussion's sake, that each bid is unique, so you don't have ties. So you get to bid what you like, but you're not allowed. Just for making this discussion easy, you're not allowed to bid the exact same number as someone else.
That's interesting, because I could just bid like $1 million.
Yeah.
And nobody's gonna want to pay this, so I get the correct.
It's a way to you could always win the bid by as long as you know that you're willing to pay the second price. Then you can bid some outrageously large numbers such that you win the bid, and you only have to pay whatever the second price is.
I mean, I guess the counter though, right, is like someone could get annoyed that you did that and then bid $999,000.
Right.
So,
again, everyone's strategic. Thank you. Yes, exactly this. So the other actors, someone sees, particularly if, say, you're not the last person bidding. Again, we're making a simplistic version of some ordering thing. But yeah, exactly this. Someone can be adversarial against you, and then now the second highest bid is some really high number, much, much higher than your value. Okay. Is that clear as I guess, a counter strategy from some other actor who, again, their self-interest is to win the bid, and other people lose the bid as the ideal outcome. Okay. You could also imagine, I guess, that could be a mismatch between what the seller thinks of the value for the item and the set of participants who are choosing to buy. And so one way to mitigate this issue, it still has to be useful for other things, but one way to mitigate the issue of perhaps a value mismatch between all the buyers and the seller is to have a reserve price. So instead of, second price wins, there is a minimal price of selling, right? So the seller has decided, at least their sense of the value of the item. And so unlike the generic second price, the highest bidder wins if their bid is higher than whatever the reserve price is. So this avoids adversarial collusion that may, for instance, lead individuals to bid collectively too low, or if their values just mismatch. So this allows avoiding that particular issue between the set of buyers and whoever's selling. If their bid is high enough, they win, and the actual price that they pay is the maximum of the reserve price and the second price. So if the second price is higher, they win. Yeah, they pay the second price. If the reserve price is higher, they pay the reserve price. So this mitigates some of the gaps in value. It also mitigates partially some of what you said. At least, the seller is guaranteed to at least meet their reserve. So it mitigates some of the adversarial behavior that we talked about, yes.
The reserve price is hidden from the bidders?
You could do both. In this setting, it's known and public. But yeah, you can have either mechanism. And interesting in different ways, as you might imagine. We'll talk a little bit about amount of information available as we go through. Cool, good question. So yeah, a literal example with, I guess, some numbers to ground it. Or any questions on the setup? Okay, so now lots of people have worked on this. We're going to see lots of Nobel Prize winners, actually. So it's, I think, one of those areas where economics, I guess a lot of them, not surprisingly, economics Nobel Prizes, have worked specifically on mechanism design kinds of questions. So in particular, there's the second prize auction is sometimes also called the Vickrey auction. This work done in 1961 eventually led to a Nobel Prize. And there's been a bunch of follow-on work in the CS literature engaging with this question. Again, adding in some of what we've talked about a little bit, things about computability, things about learnability if there's a learning algorithm in the middle, strategic behavior of different agents, different settings, things like that. Okay. A bit more formally, to set things up, suppose we have M items and N buyers. And each buyer has some value for every possible bundle of items within a set of items. So however one defines the bundle. And so sometimes this list of value across all the set of items is sometimes called the buyer's type, which is, again, just you can think about this as a vector of enumerated of the value for every possible bundle of items within the set of items. Okay. And so, for instance, in our coffee example, as we already went through, here's an example potential buyer. So the set of items, coffee and cupcake, value for nothing is 0, numbers for every combination of things, like we already talked about. And so their type would be just this list of values for different items, and you could have this across all the different buyers in the system. Okay, and so in the sales setting, the mechanism is defined by two main functions, which is allocation, which is what some process that decides which buyers get what items, and then a payment, which defines how much each buyer pays once they're engaging in the mechanism. And as mentioned, often, definitely you can, given this setup, you can always measure the revenue, which is, again, generally thought of as sort of the sum of patients across all the buyers that participated in this mechanism. And again, you might think about this as the targets of like what you want to maximize, or you could have other things, as we alluded to briefly, that you want to maximize. It's also worth saying that depending on the specifics of the mechanism, often buyers can bid whatever they like. As mentioned, often they will be incentivized to be strategic. Because of this, they may bid something that's not their true value of an item. And so we'll talk through implications of this and what some of what is known about designing mechanisms to make it more likely that buyers might bid their true value for the bundle, the set of items. Questions? Okay, so some properties that you might want, and one that I thought of as like the sort of core things that often one wants when designing mechanisms. One, we covered this in social choice briefly, this idea of incentive compatibility. This is incentivizing agents so that they bid their true value. They're likely to bid truthfully, which has multiple potential, from our purposes as a designer, this is our goal. And you can think about this purely in this sort of economic revenue maximizing sense, or you can also think about this in terms of eliciting preferences. So the true value you can think of as like, the true value for the items. And this is like the target that you might be interested in this elicitation mechanism. Another thing that you will often want the mechanism to do is, and this is often from the buyer point of view, is to be individually rational. So if they're strategic and they're looking to maximize or whatever in terms of engaging the mechanism. You ideally want to set things up such that they have nothing to lose by participating in the mechanism versus not. So essentially, this makes it, reduces the barrier to entry for them to choose to engage in the mechanism. So we'll talk through some of this in a second. So incentive compatibility is also another canonical idea. So yet another Nobel Prize in 2007, originally introduced by Hurwitz in 72. And again, as mentioned, so formally, primarily in sort of economics literature, but then engaged with quite a bit across lots of other literatures, increasingly computer science literature. And so formally, I guess state a claim and then do a sort of informal proof of the claim and pointers to sort of formal proofs if you're interested. So the informal claim is that the second price auction, which we talked about briefly, which is this idea that you collect a set of bids and then the winner is whoever has the highest bid, and then what they pay is the second highest price. So whoever bid second number. And the claim here is this is incentive compatible, which means here that every bidder will maximize their utility by bidding truthfully. So the claim here is that if I choose this as the auction mechanism, the bidders are incentivized to bid their true value and cannot do better by population sense overruns by trying to be strategic and bid something that's different from their true value. Okay, so let's go through this. The utility here is again measured as the value that they place on the particular item that they end up winning, minus the payments, so this gap, times or indicators of selecting for whether or not they won. So over a set of, assuming there's a single winner, this is just the value minus payment of the winner is the sort of utility for an individual. You can average this over population. Okay, so why might this be true? So we talked through some strategies, and there were some version of like, should I bid over my value? Should I bid less than my value? Let's talk through the first one. So one idea is to strategically bid bigger than your value because you know that you're not going to actually have to pay what you bid. You're going to bid, you pay the second price. So why not do that? If they would have been a winner because they had the highest value, then they're still the winner, whether or not they bid above their true value. So just to be clear on this, we have a set of bidders across, say, on this line, a bunch of bidders that have some set of prices they bid for an item. Suppose in this list, individual K was going to be the winner of this auction because they had the highest value for the item. Then if they bid something above their true value, they're still going to win compared to the other situation. And the price will not change. So they've got nothing from doing this extra work of bidding higher than their true value. So the claim here is that in a setting where, again, they would have been the winners anyway, there's no additional benefit to bidding something higher. Separately, if they were going to lose the bid, meaning someone else had a higher value for the item, then they might end up winning by bidding something higher than their value, but then they pay more than their value. And so this difference here goes from positive to negative. The utility becomes negative. See if this works. It works when it likes, and now it's not one of them. Let's try the cursor. Okay, so this evaluation of the utility, which is this gap from what they truly value for an item versus what they pay, is assumed to be positive, right? Because you're assuming that we're sort of paying less than or equal to the value for an item. But if they bid really high, then everyone else can bid whatever they like. And so there's a good chance that if they bid high, then the second price winner will also be ahead of their value. And so they'll end up paying more than the value. So you have negative utility in that situation. And so from the point of view of the individual bidder, the claim here, informally, again, can we state it formally, is that there's not a benefit to bidding higher than the value from an individual actor point of view in this mechanism. Okay, The other strategy is to strategically, overusing strategy here, but you could choose to bid below. So we can go through what might happen. So again, you can argue, suppose they would have been the winner, so they had the highest value across everyone. Now, if they bid below their true value, then their true value may end up lower than someone else who has a higher true value that chooses to bid their true value. And so they end up losing the auction. And so they lose the item. And again, they get zero utility. So again, in terms from the point of view of the participant or the buyer, you can have positive utility. The value is higher than what you pay. Have zero utility, which you can just think of as they don't win, or they pay the same as the value. Or you have negative utility. You overpay above your value. And so the argument is, if you're trying to maximize this, what are the different strategic decisions to make and what their impacts might be. So, if you bid too low, then you might lose an auction that you might have otherwise won. And so you end up getting negative utility or zero utility from losing the auction. Sorry. Okay. Separately, if you're going to lose anyway, because other people have higher value for that item than you would, then you're still going to lose. Reading it in real time, I might have used slightly different words, but same thing. If they're going to lose, they'll lose the auction, and so the utility is zero. And so it's not from their individual strategic point of view. They're not essentially, they don't do any better participating in the mechanism by strategically choosing to bid lower, as argued here, or higher, as argued in the previous slide. Thoughts, questions? Okay, so second prices, again, if you've ever engaged in anything related to auctions, you've almost definitely heard of it. It's sort of this property in particular has led it to be, I think, one of the more successful strategies. So we'll get to this in a little bit. It turns out that lots of the search mechanisms use second price. It turns out that they're not fully well matched in that second price is for a single item being bid on. Whereas in search settings, typically you're bidding over a bundle of items. So it turns out, we'll spend 2 minutes on it at the end, but there's some mismatch there. That said, second price has had a huge impact in practice and is like essentially the leading auction mechanism, partially because of this claim, this idea that for a rational buying agents, their best action is to bid their true value for the item. So strategically trying to bid above the value or strategically trying to bid below the value in a population setting would mean that they will do worse than if they bid their true value. Yes?
Is it also the best thing for the one that sells the item?
Not necessarily. And in fact, we'll get to this in 2 seconds. So no. So the claim here, the question was, as I understand it, is second price the optimal mechanism in terms of, say, revenue, if you're trying to maximize revenue? And the answer is no, for a single item auction kinds of bids, but it is the optimal it does satisfy this property, but it's not the revenue maximizer mechanism. That's correct. Okay. Okay, another property which we mentioned briefly is this idea of individual rationality. So again, another nice property of second price is that it's individually rational. The claim, again, stated informally, and I'll point you to references if you want to read more carefully or get a formal proof, is that each bidder is no worse off participating than not when they choose to bid their true value. So again, in terms of their individual, rational choice of participating, not participating, they don't lose anything by choosing to participate if they're going to engage in this using their true value for a set of items. Just repeated that. So the way to see this, if the price of the final price of the item is less than their value, they pay nothing, or their payment is smaller than value. Sorry, Actually, that's the claim. Yeah. So bidders pay nothing, or their payment is smaller than the true value for the item given participating. Because again, remember, if they bid their true value, then they either win the auction and pay a second price, so they have positive utility, or they lose the auction, but someone who had a higher value for the item will win the auction. And so strategically, in terms of engaging in this, they lose nothing by choosing to engage, as long as they choose to use their true value. Is that clear? I'm feeling a bit word salady, so I want to make sure it's getting across clearly enough. Cool. All right. Slightly more formally in the way often these analyses are done, need a little bit more information. So generally, you can think of bias values as defined by a probability distribution. So think of these as samples from some distribution over the bundle of potential set of items. And from that perspective, there are a bunch of different ways that you can analyze IC properties. So the first is what is often called, and I just list these as definitions more than engage in detail. The main thing to get away from here is different levels of information about the rest of the mechanism that each bidder might have, and agents might have. So one analysis is purely distributional. So you presume some distribution over values across items from all the bidders. And so this is often called ex ante IC, or incentive compatibility. So the goal of the mechanism designer here is to ensure truthfulness and expectation over bidders' values, given knowledge of distribution of that where the values are sampled from. Slightly stronger notion is called ex interim. So now bidders know their value and distributions over others' values. And so you want, even in this setting, some notion of truthfulness to be the dominant strategy, like the best thing to do to engage in this mechanism that's called ex interim IC. And then finally, it is called ex post. There's a term ex post IC, which is, you can think of as the strongest version. So now I don't know distributions, I know actual bids of everybody. I know actual values of everybody. So I know essentially what everyone values for all the items. And you still want, or you'd like that the bidders should still be incentivized to be truthful in that setting. So you can think about this as sort of different amounts of information that bidders might know and definitions of IC in these different kinds of settings. And so you see this when you look through the literature on incentive compatibility. Okay, so there are lots of mechanisms out in the world, different kinds of purchasing systems. We've talked through auctions, we've talked through I guess first price in general. Many of them, I guess, either known to not be incentive compatible, or in some settings, they're sufficiently complex that like a full analysis has not been done yet, so it's not known if they are. So common ones, things like first price auctions, which is often what display ads use. So you pay the price. The winner pays the price that they bid for many display ads. And, if you don't have this, then what this means is that, a strategic actor may do better by picking a bid that's not their true value for the thing you're selling. Right? So again, that's the potential loss, the potential cost, I guess, for the mechanism of not having incentive compatibility is that you lose the claim or the guarantee that participants are incentivized to bid their true value. Okay, so things like first price auctions, we talked briefly. Many sponsored search ads, so things like what Google uses, are called generalized second price auctions. The main difference is, again, the first price IC claim is for multiple bidders, single item. And search ads, you're bidding over like ranking, like multiple placements of search ads and multiple items. And in practice in general, so I think the following is known. So people still use, most search ads still use generalized second price auctions anyway. People have shown that there are strategies that can game generalized second price auctions. So it's known not to be incentive compatible. I think yet it's still probably the most popular deployed algorithm. So it's maybe an interesting, fun cognitive dissonance that, is this strong property that we want? There is an idea that's inspired by a different setting where we have very strong guarantees. People transfer it to this new setting. The guarantee is lost, but it's still used in practice. Okay. And also lots of other kind of like more complex combinatorial auctions and things like that are either known to not be incentive compatible or not known because the analysis is incomplete. So some of the issues include that figuring out the values might be expensive. So this is a sort of computational argument. Issues with like the rules and ease of explaining. There might be some leakage between the bidding process and the sort of auction mechanism. So for instance, using bids to tune future parameters of how you might bid in the future often will change things, depending on exactly how the mechanism is designed. Or agents are not risk neutral. And so the premise of the whole thing means actually like invalidates the assumptions that we're making about agents participating in the mechanism. Okay, so there's a bunch of work in literature. I also wanted to mention that while I've stated this as a property, there's a bunch of work that also tries to make claims about approximate notions of incentive compatibility, so some measure of departure from it. I won't engage at all, but I'll point to references if you're interested to get more details on other notions of approximates. I see. Okay, so that's most of what I wanted to say on incentive compatibility. There's also, you can say similar things about individual rationality, purely here in terms of, so remember here, this is this argument about whether bidders are worse off choosing to participate in your mechanism or not. And so an IR mechanism has the property that each bidder is no worse off choosing to participate. And you can analyze this, again, at different levels of bidder information. I'll skip the next one. Okay, so there was a question about actually maximizing revenue. So this is known for single item auctions. So this is due to Meyerson, another Nobel, I think a third Nobel Prize. I think I only had 3 in this. There might be others related to this. So in 81, showed the revenue maximizing single item auction, which is a somewhat more complicated second price. We'll talk through it in 2 seconds. So we'll answer your question. So the issue with the second price auction, as already identified partially, is that a stronger bidder always pays the weaker bidder's bid. And so the revenue from a seller's point of view depends much more strongly on, I guess, the values of the participants. And you could argue that from the seller's point of view, what they want is the true value of the actual maximal bid. But if they ask for that, so if they ask to pay the top bid, then you lose incentive compatibility because there's strategies that you can then use. So if you like, there's a trade-off that needs to be made. What the seller wants is to maximize their revenue, so get the highest price. If they knew all the values, then what they would pick is the buyer with the highest value. If they do that, then this means your mechanism is vulnerable because those buyers can be strategic and actually then bid something else and end up paying less. And so there's this sort of yin-yang weirdness thing that's happening where the obvious mechanism of just paying the highest price loses strategic usefulness, but the mechanism that is known to be strategically correct, which is, again, the second price thing, leaves revenue on the table. So it has this gap. And so Meyerson suggested a alternative strategy and then showed that this keeps IC, but then also maximizes revenue. So it's a relatively simple idea. In a distributional setting, let's assume that bidder I's value has a distribution with a certain PDF, call it F, say supported on 0, 1. So we just normalize so that the values are between 0 and 1. And so in this setting, we're going to define a set of virtual values, which are the difference between, this is I guess a functional definition. So given the distribution of values for each individual, I'm going to define this function, which takes that distribution, which takes that distribution and computes a new property from it. So this is, what thing I'm going to plug in is the value. So I just go ahead and talk about this in terms of values. Because the value minus some normalized notion of distribution of values for that individual bidder. Okay, so once you compute this, you're going to solicit bids from across all the buyers. And the procedure is first you check if all the virtual values, these computed quantities across all the items for each bidder, if they're all less than 0, then it means, which also then means that the gap between the value and this sort of CDF correction is negative, then you don't allocate the item. So the mechanism ends. If there's at least 1 that's greater than 0, then you allocate the item to the buyer with the highest virtual value. And then they pay a thresholded bid, which is computed as the sort of inverse of this forward function. So you can look at the definition. So this is a variation on second price. It's actually probably worth saying. So this is this maximum, messing up the mouse here. This maximum is computing all the virtual bids for everyone else and looking at the maximum that's not the winner. So it's effectively the second price for the virtual bids. And then it has to be greater than 0, which is the first criterion here. And then you do sort of a inverse transformation back to the values, and that's what they end up paying. And what Meyerson showed is that if the bid is set up this way, so this has properties that look a bit like second price, as you might see, because the price they actually pay is the maximum virtual bid for everyone else, apart from them, assuming they're the winner. So what Meyerson showed is that this keeps IC properties, so you remain incentive compatible, meaning the optimal strategy is still to bid your true value. Yet you can show that this is the revenue maximizing strategy. So this will maximize from the seller's point of view, the amount of revenue that they can get while ensuring that all the bidders are still incentivized to bid the true value they have for each item. Okay, so in a simple setting where buyers' values are IID, so they'll have the same distribution, it turns out that you can convert this into a standard second price auction where you have a reserve price of phi inverse of 0. And you can sort of kind of see this because the virtual values will all be sort of offsets of each other. And the actual price being paid will look like this inverse function maximum of 0. So, at least from a colloquial point of view, hopefully it's clear why this is connected. Yeah, okay. And there's also work, just alluding to it, of the same item but multiple units of an item and how to think about optimal revenue maximizing incentive compatible auctions for that setting. I'll let you look at the reference if you're interested. Okay, so beyond that, it turns out that we know how to do single item optimally in terms of revenue maximization in IC. It turns out, at least I think it's still true to my knowledge, unless something happened since when I looked up this literature and now, which is minutes or hours maybe, that we don't know how to do even 2 items optimally. So this may be a bit surprising, but just stating as a statement of fact. There's a bunch of work that has engaged with this, both in the economic side and in computing. And so meaningful progress on thinking about these questions, but maybe a hard, interesting problem if someone is theoretically inclined and wants a really hard problem to solve. This might be a fun one. And maybe surprising as well, right? Perhaps, given what we said at the beginning and some of the description of the overall setting. So this also engages with more and more as people have connected this to machine learning settings. So in particular, as you might know, many of the modern, say, ad bidding Infrastructure has learning models under the hood, which help, say, predict prices, predict placement. There's a bunch of learning under the hood. So there's a bunch of work that tries to connect learning methods with mechanisms and ask questions about their interaction. So, for instance, there are aspects that try to use online learning to ask questions about sort of revenue and bidding. So, you might think of, say, a buyer that, say, potentially might choose to buy an item multiple times over the course of a week, for instance. So they arrive, either them or for a population of buyers, and there's some price for the item, and they might choose whether or not to buy. So this is the version of a fixed price type of setting, like I mentioned at the beginning. But you can also imagine doing this within other kinds of interesting mechanisms. And so there's a bunch of work engaging with how to do learning things in this setting. So some of the questions you might be interested in asking include, so learning questions, regret, as you know, is one of the main ways. We've already covered it in the Bayesian optimization work, for instance, that we did last lecture. So this difference between the cumulative revenue for the seller versus the best price that they could have gotten in hindsight. And so there are a bunch of settings where this has been studied. There's work engaging with potentially adversarial buyer values, stochastic buyer values, maybe somewhat easier cases where buyers are seem to behave truthfully, various kinds of strategic behavior by the buyers. Other work, and maybe much more directly related to us, are things like mechanisms for where the buyer has to learn how to bid. So they're engaging in the ecosystem or the mechanism over time, and based on the interaction and sort of signals that they get from the mechanism. And also, so this is what they get from the seller and what they learn from the other participants. They try to update their process for learning how to bid. So, for instance, a simple version of this is like a learning to bid setting where at the beginning, the buyer knows nothing about the values for items. At each round, they only learn values for items that they actually win. So they choose something, and then if they win, they learn the value. If they don't win, they don't learn anything. And so the goal is to compete with the best fixed bids in hindsight. So the optimal strategy is if I knew sort of true values and I could actually bid those. And so the regret setting is, again, if I knew the optimal fixed bids, what is the gap from that strategy? Similar to, again, the way we've talked about regret over the past couple of lectures. So same idea. Other interesting aspects of this, so there's something called profit inequality kinds of problems. So here, buyers arrive in adversarial order and have random valuations. So again, an interesting setting. People have done a bunch of interesting work, many of them in competing venues, asking about like how learning, again, engages interactive mechanisms. Secondary problems where the naming is meant to allude to buyers arriving in random order. So the gap here is, again, the two things to intervene on are the order in which buyers arrive and then the valuations. So the distinction here is in profit settings, the buyers are adversarial in terms of ordering, but the valuations are some generic distribution. In secondary problems, the buyers arrive randomly, but the valuations are adversarial. They're thought to be some notion of worst case. And some people have done lots of work in trying to engage with how learning interacts with mechanisms in those settings. Also related to stuff we've covered in class. So, you can ask about learning with various kinds of revealed preferences. So similar to some of what we already discussed in economic decision making. But here, pricing tied in with, or I guess you get to observe people's individual buyers' actions over iterations. And then you want to predict their behavior in the future, and then think through what the mechanism might be for pricing in these settings. Okay, so lots of interesting questions, many of them learning theoretic. So things like how many training examples do you need? So standard kind of sample complexity kinds of questions you might ask in a learning setting. Algorithmic questions, how do I learn a preference function in this setting that captures the buying behavior, and how does that tie to mechanistic choices? lots of fun work in this area. Again, as mentioned at the beginning, this is a full, rich area, which we're not engaging with. Hopefully we can pull nuggets of ideas here for how we think about the purpose of this class. And then I think there's an opportunity for a deep dive for people who find this kind of material interesting. I think there are lots of lessons. The reason I'm presenting this actually is I think there are lots of lessons for the task of like preference solicitation and preference optimization in AI that I think is the translation is underutilized. And so I think there are interesting things to learn from this literature. One example, pairwise feedback auctions for digital good settings, which mixes a bit of elicitation, some of the online learning bandit things, a bit of mechanism design is sort of one example of all these things coming together in a preference estimation optimization setting. So this is motivated for digital goods. So things like what we've already engaged with a lot in this class, things like prompt completions, synthesized images, stuff like that. But you could also imagine using this for things like ad placements and other settings. I think in standard auction and bid settings, the market is obvious. The bidders get to know ahead of time the item that they're bidding on and something about the ecosystem, and often will know the mechanism actually as well. So they know a lot about the infrastructure. Saying, no, if I'm going to buy ads on Google AdWords or whatever, or I'm selling items on eBay, I want to sort of build those auction systems. In digital goods, you don't know how good the response is going to be until you've actually completed the process. So the work has been done, essentially. Right? So I'm looking to price, you can imagine from a seller point of view, I'm OpenAI or some other big generative model builder. I'm looking to assign some price for a certain prompt completion. This is not how it's done now, by the way, as all of you know. Right now, it's all fixed price, no auctions. But you can imagine perhaps economic incentives lead to variable pricing for prompt completions, which a reasonable way to think about going about this might be something like this, like an auction. The challenge with an auction, of course, is that I don't know how good the completion will be before I see it. So all I get to see, I only get information after I've already the seller has already done the work. And so if I was looking for pricing a signal of whether to do the work or not, in some ways this invalidates the whole idea of choosing whether or not to say complete a certain prompt based on whether the buyer is willing to pay a certain amount for it. Is this clear? Another wordsality thing, but yes. So one more time, at least for myself, even if maybe you guys, I'm seeing nods, but I'm hoping they're not just polite nods. So mechanism is that the seller of the digital good has to decide how to price things like prompt completions. Ideally, you'd want to do this before actually completing the prompt. And in order to do this, the seller has to know what the actual prompt completion will be. So there's a mismatch of information here because the seller doesn't know the prompt completion until the prompt completion is actually done. And so they don't know the value that they would have for the completion until the work is actually done, which means that the buyer can't decide ahead of time whether or not, the seller, I'm mixing bills. The buyer doesn't know ahead of time whether they want to buy a certain completion. The seller isn't able to make the decision of whether or not to sell to the buyer at a certain price because the buyer can't figure out whether this particular completion is good or. So there's this weird cycle thing of someone has to make the decision first, and it's unclear how to engage in this setting. Okay, so this is, again, related to many of the problems we've been discussing, but the main point is to argue that this is somewhat unique compared to the generic auction setting because there's this additional missing information because you have this sort of, unlike standard settings, pricing, and actually the item is actually not a real thing until the process is complete. So it makes the pricing a bit complicated.
I know I shouldn't.
Yeah, please.
I've more recently been calling this like it is used in the literature too, just information asymmetry between the two parties. Like at the very beginning, you had this like Sotheby's auction.
Yeah.
An example in that context is one time they sold a painting, and as soon as the auction was completed, the painting automated itself and destroyed itself.
All right, I remember this. It was a recent thing. Yeah. Okay, that's a fun one. It's I guess if the buyer knew ahead of time, they might have changed their evaluation for. My memory is that this wasn't known, right?
This was a surprise. No.
Okay. Do people know the story? It's a real thing. So.
NFT token. Is it related to some NFT token?
No, this was a real painting. So it was a.
It just like as soon as it was sold, like it was actually like a paper shredder. So,
Yeah.
like it automatically.
So the art included destroying the art. You're paying for the art being destroyed in front of you. And so, as an artist, you can imagine this may look completely reasonable, but from a buyer's perspective, this may seem adversarial. But the point here is that, in terms of limited information, I guess is a good way to say it.
Yeah, but this happens. Right?
Indeed.
Sometimes if I talk to O1 or something, you put in a huge prompt, it thinks for like 2 minutes, and then it spits out 0 tokens.
Yeah.
Indeed. Okay. I think that's a great, actually very modern. That was not available when we did this. That's a great example, indeed, of this issue. Okay. So what needs to happen? The bidders have to submit offers. And you can imagine this in a competitive setting where the thing that's forcing pricing is, say, computational resources, right? So you have to decide, you get 1 billion requests, you have to decide a small subset of these. Again, this is not what's happening now, but you can easily imagine the way things are being used. That like this may be part of a, if there are resource constraints, then one way to mitigate resource constraints is to have adaptive pricing that may be tied to people's value for the completion. And the challenge here is, again, this information asymmetry. So bidders have to submit offers to fulfill requests before actually seeing what the responses are. And then there's this resource behind the scenes that needs to be allocated. So what completion do you make? So the question is trying to decide fair pricing. In the ideal setting and in standard, what you don't get as much as you'd get in a standard auction setting is, again, users don't having complete information, and so you want to think of some way to improve or increase the user information to form their valuation. And you'd also like for the whole mechanism to be incentive compatible, as we've already discussed, so that bidders, whoever is engaging this mechanism, is incentivized, or their optimal strategy is to bid the true value for the completion, which ahead of time they don't know. This is, of course, a challenge. And so the setting, more formally, is that we have a set of users. We have the ith user at time t. This exists a mechanism that will choose to fulfill or not fulfill a request that comes in. So this is request X for the ith user at time t. The agents get utility, some true utility mu it, and reported utility RIT for the allocation. So whether or not the request is actually completed. And we want to design an auction so that, given only observations of request and reported utilities, good here we'll define as sort of utility maximizing and incentive compatible. So you want that, again, from a individual and like revenue utility point of view, we maximize globally, as mentioned before, and then from a individual sort of stakeholder point of view, they should actually state their true value as opposed to try to lie. So compared to a lot of the existing work, some of the gaps include often we assume that agents know their value for outcomes, as mentioned in some of the discussion earlier. You also have uncertainty that plays a big role here. particularly in these kinds of stochastic generative model settings. So the mechanism now needs to be dynamic in setting where the agent can't know the value ahead of time, and the value might change over time based on context and things like that. And in addition, outcomes may be uncertain in various ways. So as you might imagine, so there's a challenging problem and somewhat distinct from at least what we've covered today in terms of existing standard mechanism settings. So the proposed mechanism is based on pairwise preferences and other kinds of partial preferences. And so it's this loop of like an initial stage where you try to learn the potential value of across items. So you want to learn, ideally you want to learn a function such that you can predict ahead of time the value for a particular response request. And so this is a learning problem behind the scenes of sort of taking X and predicting the value. And the signal that you get back are set up as things like pairwise preferences or like thumbs up, thumbs down for a particular pricing. So you might ask, for instance, from the buyer, would you like this or this as a completion to your prompt? As we discussed in an example for those of you who are in that class, and I imagine the same is true here. There's settings where the buyer might prefer this or prefer that. So given the last lecture, I actually completely believe that now it may be uniform across this group. Those of you that weren't here, we did in-class pairwise, and people argued strongly for very different things. So let's just say, individually high variance. Or you could ask questions as, if I synthesize this, would you pay $2, thumbs up, thumbs down? So this thought of as like low signal responses to various kinds of simple pairwise type queries. And so the mechanism under the hood is again built on second price. But now, because the prices are not known ahead of time, we have to use prediction of the prices. Because again, you don't know the price for completion until you've actually asked it. And so there's an initial learning stage, and then the claims are sort of essentially the claim is sort of once you've seen enough examples in this setting, that you should essentially be able to predict the second price offer well enough. So predict the values well enough that if I use the second price offer for pricing, that I will satisfy all the properties that I want, which are, again, high revenue and incentive compatibility. So under the hood, the key things are learning to predict user evaluations based on responses, like the ones I just showed, sort of pairwise preference and thumbs up, thumbs down. And then, I guess that's the main thing. And then the actual mechanism being use the second highest predicted offer for a particular completion. So in real world use case, mechanism is behind some silo. I, as a user, come in, I ask for a particular completion. I give you my X. The mechanism predicts what they think the value I would have for the completion of that X, and does this for everyone in this room. And then calculates the second highest predicted offer, and then charges me charges the winner. Let's assume I'm not the winner. Whoever is the winner of that interaction. So whoever has the highest predicted offer wins the auction, and then they pay the second highest predicted offer. Okay, so this is a mechanism you can use for direct pricing. So as a way to do things in information asymmetric settings, like digital good auctions, or if like we talked about earlier, I love that example. Your auction house, and you might sell paintings that may be destroyed. I actually wonder what happened to auctions after that. It's such a fascinating story. Anyways, it's weird. I haven't followed up. I know of the story, but I don't know the rest of it.
Like that painting Bansky became so popular.
I think it was Bansky. Yeah, exactly.
In time, game came and it was auctioned much more because now it had historical.
Oh, interesting. Oh, that's fun. Okay, maybe it's that would be a fun meta mechanism here, like intentionally destroying things to raise prices. So I guess
That's the thing.
no, for sure. No, indeed.
Flash and burn.
Yeah. And I think particularly in things like art, where valuations are, exactly. Fun individual valuations. Anyways, what I wanted to say here is we applied this to maybe an interesting alternative setting where instead of trying to price items for user completions, we wanted to try for the opposite. Here, we're interested in the fact that, a lot of what needs to happen for many of the modern generative AI systems include labeling potentially toxic or psychologically difficult material, both text and image completions. And one of the ways you could imagine engaging in this, and I want to be careful to state that this is not a perfect solution. This may be useful as one of the levers to engage with potential psychologically damaging conclusions. Is that if you think that you can connect individual harm to some economic value, and again, this is not a normative claim that this is necessarily a good idea, but in certain settings, this may be reasonable. If that is true, then you can imagine paying people tied to how much they might suffer harm for a particular completion. So, if you're going to do a particular completion and it's going to be one that causes you significant harm, that you can imagine the price for that labeling might be much, much higher than for either the same individual with a less sensitive completion or a different individual that just has a different profile and different sensitivity to different amounts of difficult labeling. So there are a bunch of ways to engage with this question. Again, I'm repeating maybe for a third time. This is thought of as a interesting proposal, not as this is the solution for everything. I think there are lots of levers to engage with asking this question of, can we curate the labeling ecosystem to be less psychologically damaging? I think that's the key question. But one interesting potential lever is using adaptive payment systems that adapt to potential individual risk or harm from a particular labeling. And so this can be tied, for instance, you can make a fairness argument. So you can think about this as like fairness. You might argue, for instance, that fairness means that your payment should be correlated with how much harm you might be suffering from engaging in that task. And so even here, you might imagine there is some incentive to be strategic if you were just going to ask people. And so you might imagine trying to come up with a mechanism that still gets at the same question of can I actually accurately evaluate potential individual economic harm or economically evaluatable harm. Let me be careful here in this kind of setting. So the way to do this with this mechanism is you treat this as a reverse auction. So instead of having the values be negative or positive, they're now negative. And so you want to, instead of maximizing revenue, you want to minimize negative. I guess you still want to maximize, but now you're maximizing negative things. So you want to get things, you want to minimize the amount of negative value people have or harm people might suffer. And so you can consider applying this to compensation for various kinds of hazardous labeling. We applied this. I'll just show some results, and you can look at the paper for some of the details. So the key thing here is we wanted a mechanism that can use much less information because, again, there's asymmetric information, as we talked about. You don't get seeded completions till you've actually engaged in, you don't get seeded completions till you've actually made the query and there's been a completion. And so we want to use this sort of all the pairwise mechanisms that we talked about as a way to reduce the amount of signal that you need to learn the value from each of the stakeholders. Under the hood, as mentioned, there's a prediction system that tries to predict the potential value, in this case, negative utility, from a particular completion. And then we do the second price thing just like before. And this is compared to other generic things that you might imagine doing. One generic thing is that you get to observe values and you just do a regression and then predict directly from there. Another is usually uniform across the set of stakeholders. And we show that using sort of the pairwise feedback thing uses much less information and is in terms of overall regret. So this gap from sort of best possible allocation to predicted allocation is much lower than, say, a uniform allocation. So one that doesn't take individual values into account. We also looked at other kinds of losses. I'll defer. Actually, I think we're at time. We show again that across the population, you have better distribution of a certain notion of welfare loss. Okay, so we don't have time for the Q&A as always, unfortunately, but I'll just quickly go through it. So mechanism design, design rules, so the strategic behavior by participants still leads to a desirable outcome. Here, we're mostly interested in how it engages with truthfully eliciting stakeholder preferences or optimizing. So eliciting or optimizing, I'll engage. I'll update that a bit. Some of the main evaluation measures include incentive compatibility, individual rationality, and then often revenue or utility tied to that, or some other notion of social welfare. Next lecture, we have an invited lecture by Joseph J. Williams, who will talk about ideas related to this, engaging and using some of these things for like A/B testing and other kinds of online learning, preference optimization settings. Okay, thank you. I should also mention, so a bunch of this is borrowed from a great tutorial by Ellen and a bunch of other collaborators. So I will strongly push to see some of that material if you're interested. And then Tim Roughgarden, who is now at Columbia, teaches an excellent course on if you're interested in more of those details. And the material here is roughly lecture 1, 2 of what he covers.